by A by itself, by H when B is equal 3 to 0. Square again, so that this is already working code for our problem of binary exploitation. You can use it. And this if turns out unnecessary. If you have 3 to first power and you analyze this piece of code, it will run 3 to 0th power and then multiply your result by itself, so it will be 1 times x. hey, anyway, hey, this is not this computer record.
Hello everyone, welcome back. In this presentation, we are going to see a very interesting topic, the modular exponentiation. Let's see the part 1 of modular exponentiation in this presentation. Let's start the session with the outcomes. Upon the completion of the session, the learner will be able to understand modular exponentiation with examples. Let's directly dive into how formed of b. Mod m is not for b, it's for a power b. Okay, for the whole term we have mod m, and that's why in order to avoid confusion we use brackets. So whenever it is a power b mod m, it means this mod m is for a power b only, not simply for b, it's for a power b. Let's see some examples. The examples include number 1, it's 2 power 33 mod 30. Let's see one more example. It is 3 power 100 mod 29. Let's first start with example number 1. The question is, solve 23 part 3 mod 30. So we are going to solve the examples from the base level. Firstly, we will start with some simple examples, then we will progress to some complex examples. Firstly, I am starting with 23 part 3 mod 30. It's also easy to do this. You can take a calculator, you can perform 23 part 3 and you will get the result. Then divide it by 30 and whatever you get that remainder, it's the answer for this question, right? But I want everyone to try without calculators. That's the main agenda of modular exponentiation. Even big calculations can be easily performed using modular exponentiation. So I strongly recommend you not to use calculators for doing these kind of modular exponentiation problems. Just see how I am doing. So we are obviously going to do 23 part 3 mod 30, right? That's what it is given in the question. As mentioned in the previous lecture, there are multiple ways to approach a problem and there are multiple ways to get the solution for that problem, isn't it? You can prefer any approach, but please ensure that the mathematical fundamentals are completely followed. Just see here, 20, 30, the result from calculation is 7 power 2 plus 1, which is minus 7 power 3. So it is now easy, right? So minus 7 power 2 is what? Plus 49 and minus 7 is retained as such, mod 30 remains the same. So 49 into minus 7 is minus 133 mod 30. Now you can easily divide this minus 133 divided by 30. So minus 13 is the answer. I already told you, always represent the final result as a positive number. So it's so simple to convert this minus number into a positive number. This value is plus 17. Just see here, I'm not going to prefer calculators for calculating 23 part 3 mod 30. Rather, see here, I have simplified these big numbers into small numbers so that I can easily work on the small numbers and I got the result. Even if you try with 23 part 3 mod 30, you will be getting 17 only as the result. But the difference is we are just working with small numbers. So that's it about example number 1. Let's now move on to example number 2. The question is, solve 31 power 500 mod 30. Placing 31 with 1 now. Can you see here?
Hello and welcome back to the channel. This is first problem solution video of practice with Abhinav series. So in this video we are going to talk about the problem locker magic of the locker. So some of you have requested me to make a video on this. Basically what here is given is that there is a businessman uh, who has 1 rupees who sells ropes to his customers at the rate of 1 rupees per meter basically. And if we put moves towards the logic, 1 rupees at the last. For example, that n is equal to 6 means he has 6 meters of rope he will sell with 6 rupees. So for 6 rupees, first of all he can sell ropes in 6 parts. पहले वो 1 रुपए बेचेगा, फिर 1 रुपए बेचेगा, फिर 1 रुपए में ऐसे करते करते 6 बार वो 1 मीटर रोप बेच देगा. But like this, when जब वो 1 रुपए डालेगा लॉकर में, then he will get only 1 rupees at the last. Because 1 into 1 into 1 into 1 is only 1. For example, he sell by 2 उसने 200 मीटर के बेचा 6 मीटर को. Then he will get 8 rupees. Why? Because if we multiply 2 into 2 into 2, we will get 8. But if he sell it like 3 into 3, first 3 meter, then 3 meter, then he will get 9 rupees. So maximum क्या हुआ? Maximum हुआ 9 rupees. Okay? एक और एग्जांपल लेते हैं. For example, n is equal to 18. So अगर वो देखो 1 रुपए बेचेगा उसको 1 रुपए मिलेंगे, which is 512. बट अगर वो 3 करके बेच रहा है तो 3 to the power 6 कर सकता है. क्या कर सकता है वो 3 to the power 6 कि मान लो हमारे पास 100 दिया हुआ है 100 रुपीज. तो मे भी आप ये सोचें कि 100 रुपीज दिए गए, हम 10 को 10 बार कर लेंगे. तो जब 10 को 10 बार करेंगे तो 100 ही आ रहा है सीधे सीधे, कोई बात ही नहीं है. या आप सोचें कि 5 को 20 बार कर लेंगे, 5 की पावर 20 हम लोग 5 पर लेके डालेंगे 20 बार. ठीक है. अगर हम लोग ये सोचेंगे 5 को 20 बार कर लेंगे, सो लेट मी कैलकुलेट 5 to the power 20. Just give me a second. Okay, so the value of 5 to the power 20 is, it is a very big number, fine. It is a very big number. So it is something about 13. So it is something about n into 10 to the power 13. Okay. Fine. But when we are making it like 3 to the power, how many times it is possible? 32 rupees. 34 किसी भी नंबर को 1 से मल्टीप्लाई करो कोई मतलब नहीं, बस मल्टीप्लाई की वैल्यू तो 3 है आंसर. और मॉड करना है, मैं मॉड करना हूं काफी बड़ा वो लास्ट में है. हम लोग n+1 ठीक है, बात समझ में आई. इस तरीके से हम लोग उसको कर रहा था. एक 3 और निकाल लिया देख सकते. मेरा भी काफी बार के काफी देर बाद हुआ था ये एक्सेप्ट, बिकॉज ये एक मैं कंडीशन मिस कर रहा था. तो पहले तो अगर A3 से कम है, मान लो A1 है A2 है, 1 और 2 के तो सीधे सीधे 1 और 2 हो जाएगा आंसर. मॉड्यूलो देना है. ठीक है. वी आर मेकिंग इट लाइक 3 to the power how many times it is possible? 32. 3 to the power 32 means that we have 96 rupees and into 4. बिकॉज अगर हम लोग 3 to the power 33 कर देंगे 34 हो नहीं सकती है. अगर हम 3 to the power 33 करेंगे तो हमारे पास 1 बचेगा. वो तो यूजलेस है. किसी भी नंबर 1 से मल्टीप्लाई करो कोई मतलब नहीं बचता है. गलती उसको ये भी उससे छोटी है 15 पर आई इस वाले केस में जब हम 3 की पावर मान लो जो तो बेसिकली हमें जो और मॉड कर इसको हम चेक कर लेते हैं. वो 50 जो होगी वैल्यू वो होगी 1 into 10 power 15 अप्रॉक्स. सो सबसे बड़ी वैल्यू कहां पर आई इस वाले केस में जब हम 3 की पावर्स में ले रहे हैं. तो बेसिकली हमें जो भी n दिया गया होगा हम लोग उसमें 3 की पावर्स में करेंगे. मान लो जो n mod 3 है वो अगर 1 है वो सॉरी 0 है. पहले तो 0 ले लेते हैं. तो हम लोग सीधे सीधे 3 to the power n/3 कर देंगे. ये होगा हमारा आंसर. और मॉड करना है, हमें मॉड भी करना है. मॉड कुछ एक पर्टिकुलर वैल्यूज दे रखा है, क्वेश्चन चेक करना पड़ेगा. हमें आंसर मॉड भी देना होगा क्योंकि काफी बड़ा आंसर आ रहा है. तो यहाँ क्या तो हमें वो 1 लास्ट में 1 के इसको यहाँ -1 कर देंगे. एक पावर कम और इंटू 4 कर और 3 के हम लोग जाएगा और इंटू 2 कर देंगे. 2 बच रहा है हमारे पास. यहाँ पर हमारे पास 1 बच रहा था रिमाइंडर. तो लोग अगर 1 से मल्टीप्लाई करते तो कोई फर्क ना पड़ता. तो हमने क्या किया हमने यहाँ से एक 3 और निकाल लिया और 3 और 1 को 4 कर दिया. एक्सेप्ट बिकॉज ये एक मैं कंडीशन मिस कर रहा था. तो पहले तो अगर a 3 से कम है मान लो a 1 है a 2 है तो 1 और 2 केस में तो सीधे सीधे 1 और 2 हो जाएगा आंसर. जब a mod 3 is equal to 0 सीधे सीधे पावर मॉड a/3 की पावर निकालिए मॉड से. ये अगर आपको ना बताओ कैसे
In competitive programming, we often see this sentence in statements. As answer can be huge, print it modulo p, some usually prime value, and it's very common that p is equal to billion 7. It's a big prime number. Why is that, and what should we do about it in our codes? Indeed, answers sometimes can be huge. Example of that is to compute 2 to nth power, because, for example, we need to compute the number of subsets of some set of numbers, or we need to count permutations. N factorial, so n times n minus 1 times n minus 2, grows very big. Already for n equal to 1000, this is n factorial. And you would need to print this if you are asked about the number of permutations of n elements. And there are two issues with this. First is that many languages, like C++, do not support by default so big integers. You need to implement something yourself or include a strange library. There are languages like Python that do support big integers by default, but even with them there is some issue. Any operations with such numbers are slow. Even something as simple as adding them, not even multiplying, takes linear time of size of their length, then let's say the number of digits. So computing like n factorial, even though it is n multiplications, it's not O of n. It is O of n times this complexity of multiplying two numbers, and this is even slower than L. It requires FFT, or L square is just multiplying. Actually, it is big number by something small, so let's say it's just this. And this is much worse than O of n, and we cannot compute n factorial well for n equal to 1 million. It is too slow. So instead of to deal with those issues, the difference between languages and things being slow because of the arithmetic, instead of printing this value, you should print only some information about it. And then we need remainder modulo some value. 17 modulo 5 is what is left if we divide 17 by 5. 17 is 5 plus 5 plus 5 plus 2 is left. This is a remainder. We have 3 5, so 17 over 5 is 3. And in programming, we have an operator modulo for that. We write 17 modulo 5 to get that value 2. And problem author, instead of asking you to print this, they will tell you print n factorial modulo m, or modulo p. It is given usually in the statement. It would be nice to say that this is code for computing n factorial. It is not correct, because as you compute 1 times 2 times 3, this of course iterates from 1 to n, I++, so multiplies answer by every next I. Why is it incorrect? Because it has overflows as we go. Times 2, 3, 4, 5, eventually we will get this huge number. We will try to keep it in int type. Also operations would be slow if it was in Python. And only at the end we take this. This doesn't resolve any issues. It only changes output format. Instead, as we go, we need to take modulo for every next operation. It isn't though obvious why it works now. Why is it correct if we need to compute some answer and at the end print it modulo m? Why is it okay, as we get some temporary values, to also compute them modulo m? It's quite easy to explain with an example, because here not only n factorial is taken modulo m, every partial factorial is taken modulo m, and maybe that changes the final answer. Also here, with just this code, we would have an overflow. Answer must be long, or we need to cast this into long. Otherwise you have billion times billion, that overflows in C++. If I talk 2, and then so we will print value for sure in this by b, what is wrong? If values of remainders can be from 0, it's okay to leave it out, because because after the last operation, after the last iteration, this operation was already applied to answer. Every time answer is in proper interval. Values of remainders can be from 0 to modulo -1, if you ever wonder. This is also, we will print value for sure in this interval. If you know C++ and understand what happened so far, you should be able to say what is wrong with this code. Let's say the problem is there is a rectangle of size a by b, we need to compute its area, and b are huge, up to 10 to 18. So the product is up to 10 to 36. That doesn't even fit in long log. So instead, the statement also says, print the answer modulo billion7. Let's say mod is equal billion7, and somebody wrote this code you're seeing below. What's wrong with that? Just like with factorial, this already has overflow. Something of this magnitude times another thing of this magnitude is too big for long log. So we cannot just say that. Again, applying this just at the end doesn't solve any issues. Instead, it is okay, just like with modulo 10, to take both of those values modulo mod. And this is a correct code. We take a modulo something, b modulo something, and we apply modulo at the end as well. Now there is no overflow if we operate with long logs, because this number is smaller than m, up to billion7. This is up to billion7, so the product fits in long log because it's around 10 to 18. This operation, this whole code is the same with what I showed you here. Here at the bottom with 7 and 6. Generally, if we have a and b, both are in proper interval from 0 to mod -1. If they are already not huge, we don't need to take them modulo. And addition and multiplication are very easy. It's just a plus b modulo m and a times b modulo m. Just remember about casting to long log if you use ints, and assuming that mod is around billion. Subtraction is more tricky. Let's work with an example of computing 21 minus 18 modulo 10. Usually in problems we have prime modulo equal to billion7, but minus 7. But in extra line, or alternatively, take this mostly altered. And we get a non-negative value. But in most languages we need to either do this, if answer became negative, then increase mod. This fixes from -7 to 3. Either about that, you can start caring about the speed of such operations, and actually modulo operator is quite slow compared to multiplication or addition. So that version with if is faster, is more tricky. Let's work with an example of computing 21 minus 18 modulo 10. Usually in problems we have prime modulo equal to billion7. This is up to billion7, so the product fits in long log because it's It's around 10 to 18. This operation, this call, block. So we cannot just say that. Again, applying this just at the end doesn't solve any issues. Instead, it is okay, just like with modulo 10, to take both of those values modulo modulo. and this is a correct code. We take A modulo something, B modulo something, and a mod is equal billion7, and somebody wrote this code you're seeing below. What's wrong with that? Just like with factorial, this already has overflow. Something of this magnitude times another thing of this magnitude is too big for long. So we cannot just say that. Again, applying this just at the end doesn't solve any issues. Instead, it is okay, just like with modulo 10, to take both of those values modulo mod. And this is a correct code. We take A modulo something, B modulo something, and we apply modulo at the end as well. Now there is no overflow if we operate with longs, because this number is smaller than m, up to billion7. This is up to billion7, so the product fits in long because it's around 10 to 18. This operation, this whole code is the same with what I showed you here at the bottom with 7 and 6. Generally, if we have A